Good day, guys. Our topic for discussion today is about the von Mises yield criterion, or also known as the energy distortion yield criterion. There are a lot of failure criterion which can be applied to both ductile and brittle materials, but the particular criterion we will be studying today is focus more on this energy distortion yield criterion, since this is the one being used by uh, the AISC with reference to the limit state uh, aspect of most steel shapes, which is we all know are very ductile material for structural design. So I will not focus more on the derivation of the general equation of the von Mises criterion, but I'd rather stick my explanation on this dimensionless illustration on the failure boundaries defined by a biaxial state specimen subjected to uh, normal forces. Okay, so here the consideration of the von Mises criterion is actually focused on a two-dimensional uh, state of stress or two-dimensional behavior. So the representation is actually non-dimensional or dimensionless. We define the both axes as a ratio of your actual stress all over the yield stress sigma y. So for the biaxial state of stress, we will be considering sigma 1 and sigma 2 as your normal stresses, and define the elements in terms of uh, both um, hydrostatic strain and distortional strain. So which means that the total strain energy we are considering here is contributed by both hydrostatic forces or pressure and distortional forces or pressure. Okay, so let me establish first the reason why, or the critical points uh, identified by these points along the axis. Okay, so we have here one point there, another point here, another point here, and another point there. So basically, this simply means that when your sigma 1 is 0, then the maximum stress that can be absorbed by the specimen in this manner is given by the uniaxial, okay, type of loading, and for this to become 1, then the maximum stress of sigma y equivalent to sigma 2, okay, will represent your point along the x-axis. So it's true at the negative, at the y-axis. So it's true at the negative y-axis, wherein your sigma 2 becomes a negative sigma y, all over sigma y becomes a negative 1. Okay, so this becomes sigma y over sigma y. And here, your sigma 1, upon reaching the state of yield, which is sigma y divided by sigma y, becomes 1. And of course here, you have a negative sigma y, and sigma y actually be equivalent to 1. So in the 4 points that I mentioned, these are actually representing only a uniaxial state of stress, since at all points, one of the normal stresses becomes 0. So the other critical points we ought to define are these points and these points, which will simply define, okay, the failure state at a condition wherein sigma 1 and sigma 2 are both positive sigma y, which means to say that at this particular point, your biaxial specimen has all the forces in tension, sorry, okay. So this sigma 2 is in tension, this sigma 1 is in tension, okay. So when sigma 2 becomes equivalent to the yield limit sigma y, and sigma 1 becomes to the yield limit sigma y, then, okay, this point which has a coordinate of sigma 1 and sigma 2 will simply become a dimensionless point in which we divide sigma y all over sigma y, such that this becomes a point that has a coordinate 1, 1. So is true with this, but the only difference is that the normal forces are in compression, but they will be signifying a value of sigma 2 and sigma 1 equivalent to negative sigma y and negative sigma y, okay? Such that at this point again, your coordinates becomes negative 1 and 1. So the only remaining point, which is a little bit difficult to compute as of the moment, are these 2 points here, which actually is passing through an axis rotated 45 degrees from the horizontal, both the horizontal and the vertical. And these points happens to be representing the pure shear stress state condition in which the orientation at 45 degrees of the biaxial specimen, okay, which is this one, uh, represents pure, okay, shear stresses. So these are now shear stresses. So there are no normal force present exactly at this point. The thing is that the value of this is yet to be derived using some formula, an equation as derived in continuum mechanics. So if you are finished with the continuum mechanics, I hope you have passed this topic on how to determine the values of the shear uh, representing the pure shear stress state or condition. Okay, and one thing you will notice here graphically, the graph connecting these critical points, although we have not yet established what the value of this is actually a rotated ellipse with center at the origin and with major and minor axis um, rotated at 45 degrees from both the horizontal and the vertical axis. Okay, so if we consider now the pure shear stress state or condition, the failure criterion may be stated in terms of the yield stress, which will come from the three-dimensional stress equation derived from continuum mechanics or any mechanics of materials in the form defined in equation 1. Okay, so this is a three-dimensional state of stress. Okay, in general, when I say three-dimensional state of stress, I am referring here into a 3D cube, no, wherein your stresses sigma 1, okay, sigma 2, and sigma 3 are directed as such that the orientation will be a right-handed system. Okay, when you say a right-handed coordinate system, we refer to a counterclockwise permutation of values sigma 1 going to sigma 2, sigma 2 going to sigma 3, and sigma 3 going back to sigma 1. So, but the graph here is a two-dimensional state of stress. Therefore, we have to just take the value of sigma 3 be 0. So we just let the sigma 3 here vanish, and therefore your equation here upon simplification and upon expansion of this will yield to a more simpler or much simpler formula for your yield stress um, variable sigma y squared equivalent to sigma 1 squared plus sigma 2 squared minus sigma 1 and multiplied by sigma 2, upon which a pure shear state may occur when sigma 1 is equivalent to the negative of sigma 2. So this is now a point wherein sigma 1 is the negative of sigma 2 here. So this is the state of stress that is defined on the pure shear stress state or pure shear stress condition. So we simply substitute the value of sigma 1, which is negative sigma 2, or vice versa. We substitute sigma 2 as negative sigma 1, such that this equation now will be further reduced into this equation. Okay, so this becomes sigma 1 squared minus sigma 1 squared will yield to a positive, no? A positive sigma 1 squared plus becomes a 3 sigma 1 squared. Okay, so if we look into a yield criterion, we just simply use the sigma y there. If we will use for a fracture criterion, we just use a subscript u there. The point is, if we now equate your failure stress with that of the value of the right hand side in terms of sigma 1, then we can create the value of tau y or tau u in terms of a fraction square root of 1/3 of the stress, or simply 0.577 of the stress. And this value 0.577, if you divide it by Fy to make it dimensionless, will yield to the coefficient 0.577, such that the value for this a representation will now be equivalent to, okay, negative 0.577 and positive 0.577. Same is true with this. This becomes now positive 0.577 and negative 0.577. So what is now the impact of such coefficient is on the allowable shear stress that we have been using in allowable stress design, wherein your shear allowable is actually 0.6 of Fy. If you are using a yield criterion, if you are using a fracture criterion, you simply substitute your Fy with Fu. Okay, so that's it for the von Mises criterion, which represents the energy distortion theory or a criterion. Thank you very much.